This is a quantitative comparison problem, but this involves geometry. So we're given a quadrilateral ABCD, and two of the angles of the quadrilateral, angle BAD and angle BCD, are 90 degrees each. And then the values of angles DBC, ADB, and AOB are provided. The numbers are not given for these angles, but they're just symbolically denoted by X, Y, and Z respectively. And then the question basically asks for the potential relationship between X, Y, and Z. In specific, comparing X plus Y to Z. So that's all we are given in the problem. So nothing is mentioned about the sides or any other information. So this problem is elegant because it can be solved in probably less than 30 seconds if you really approach it in a specific way. Now, for one thing that we have to note, that this quadrilateral ABCD, its angles BAD and angle BCD are 90 degrees each. And that actually makes it a very special quadrilateral. Now, from the figure, it's not necessarily a rectangle, right? It's not necessarily a parallelogram, right? It's not a square. It's a quadrilateral, but just from the information that its angles BAD and angle BCD are 90 degrees each implies that this is not just an ordinary quadrilateral. This is a special quadrilateral. And the question is, what's the speciality? We know that if the sum of the opposite angles of a quadrilateral, they add up to be 180 degrees, which in this case it is, because if you take the sum of angle BAD and angle BCD, they will add up to 90 plus 90, which is 180 degrees, right? So if the sum of opposite angles of a quadrilateral is 180 degree, then the quadrilateral must be a cyclic quadrilateral. So the vertices A, B, C, and D would lie on a circle. And we can actually, approximately draw that circle out like this. And once you realize this, it becomes a very, very, quick solution. We utilize the property that the angles in the same arc of a circle, or rather the angles subtended by the same arc of a circle at the circumference, are going to be equal. So if you consider the arc DC, it subtends an angle DBC, which is equal to X, right, at the circumference. And the same arc DC also subtends the angle CAD, right, at the circumference. So going by the property that the angle subtended by arc at the circumference, or angles subtended by arc at the circumference of a circle would be equal, we can basically write basically indicate that this angle CAD, which I have marked in green, that must be also equal to angle DBC, which is X. So we can basically mark this angle also as X. Now, once we do that, we can basically note that in the smaller triangle AOD, the angle AOB, which is given as Z, is the exterior angle, and this must be equal the sum of the two opposite interior angles DAO and ADO. And what is angle DAO? It's the same as angle CAD, which we just marked as X, right? And what is angle ADO? Well, angle ADO is basically the same as angle ADB, which is already given as Y. So basically, we have Z equal to X plus Y. So the correct option in this case will be the option C. The quantities are equal. So if you know and apply this property of cyclic quadrilateral, then this becomes a less than 30-second solution. But the key here is noting that the quadrilateral that we're given, quadrilateral ABCD, because it's two opposite angles, they are supplementary, meaning that they sum up to 180 degrees. This quadrilateral is going to be a cyclic quadrilateral, and that realization is key to solving this problem very, very quickly. Because once you draw the circle, it becomes very, very apparent that you can equate the angles subtended by the arc at the circumference. And from there on, it becomes very elementary to arrive at the correct relationship between X plus Y and Z.